Right. So, about time we get into various modes of heat transfer. We had a brief stint with heat related phenomena as in thermodynamics, where we studied some fundamental laws that were related to energy aspects, uh, energy changing form from one to another, etc. Those were looked into. The temperature implications. Now, what we would look at is flow of heat and the kind of temperature distribution that flow of heat could produce. In a very general sense, we would, at least at this level, look at a one-dimensional steady state heat issue. One-dimensional steady state conditions. When I say one dimension, it means heat essentially flowing in one direction, or the flow of heat characterized by a single direction. In the sense, flow of heat could be radial. So that's in different directions, but that also in effect is one dimensional because, it's all characterized by the radial distance from the origin. So one variable characterizing the flow of heat and therefore one dimension. When I say one dimension, it means one variable characterizing the flow, that's one dimension. It doesn't necessarily mean heat flowing along a straight line. It could be flowing in different directions. Even then, it might tantamount to a one-dimensional heat flow problem. So, one-dimensional and steady-state conditions to begin with. We might take a little bit of a detour and get into transient conditions also for heat flow, but a simplistic model so that we have a hands-on understanding with the basic equations and stuff related to heat flow. When I say steady state, it means at a given point, x, y, z, the temperature is time independent. That's what I mean by steady state. It could vary from one point to another at a given instant, but at a given point, it's time independent. That's what we'll seek to deal with. At a given point, time independent, right? Now, so three modes of heat transfer. The first one, for example, is what's referred to as conduction. The first one is conduction. This is related to flow of heat in material medium, where if, let's say, this part of a medium, this is a certain medium, and a certain region of the medium, say, I agitate thermally. A certain part of a medium, I agitate thermally. I increase the temperature. When I increase the temperature, then the vibration of the molecules about their mean position will increase. The vibration of the molecules about their mean position will increase, right? Now, when the molecules vibrate more vigorously about their mean position, then what they end up doing is they share their kinetic energy with the neighboring particles. And those particles in turn share the energy with their neighboring particles, and so on and so forth. And in the process, what constitutes is a flow of heat from a region of high temperature to a region of low temperature. And this mode of heat transfer that does not involve bodily movement of the particles, all that it involves is sharing of energy because of increased amplitude of vibration of the constituent particles, resulting in what's referred to as flow of heat. This form of transfer of heat is called conduction. The particles don't move bodily away, but they vibrate about their mean position and share energy with the neighboring particles, resulting in flow of heat. So that's essentially conduction. So we'll deal with one-dimensional flow of heat in conduction. Now, suppose now, so there are certain rules associated with it. There are certain rules associated with it. There is something that we refer to as heat flux. Heat flux. That means it's like the heat flowing perpendicular to area per unit time. When I talk of a heat flux, let's say this is a certain area A, and this is heat flowing perpendicular to this area, then the amount of heat that flows per unit area per unit time, the amount of heat flowing, heat that flows per unit area per unit time, heat flowing per unit area per unit time, that's referred to as heat flux. That's referred to as heat flux, or watts per meter squared. Watts per meter squared, right? Heat per unit time is watts. Per unit area is going to be watts per meter squared, right? That's going to be referred to as heat flux. Now, by experiment, out of empirical considerations, it has been found that, let's say, there is flow of heat taking place in this direction. Now, at a distance x from here, let's say, if I took a small cross section dx, and the temperature changed by an amount dt over dx, then the heat flux associated with this cross section will be proportional to dt dx. It's found that the heat flux flowing through this cross section is proportional to the temperature gradient at x. The heat flux at x will be proportional to the temperature gradient at x, dt dx at x. In fact, dt dx is a negative number because temperature is decreasing with x. If I'm talking of heat flowing in the positive x direction, then the temperature is decreasing with x. dt dx therefore will be a negative number. We then say that the heat flux associated with this cross section at x is going to be some constant minus k dt dx, This minus, because dt dx is a negative number, this minus will make it positive, referring to q flowing in the positive direction of the x-axis. Now, as far as this k is concerned, it's a property of the material medium. It's a property of the material medium. As far as this k is concerned, it's a property of the material medium. It's a thermal property of the material medium, an intrinsic basic property of the material medium, and is called the thermal conductivity. Of the medium. Now, as far as this k is concerned, different cross sections in general would be at different temperatures. K, very realistically speaking, is a function of temperature, will depend on temperature, but it's a very weak function of temperature. K is actually a very weak function of temperature. So for all practical purposes, we take K to be, let's say for regular applications, we take K to be temperature independent, to be almost a constant, independent of conditions like temperature, etc., temperature, pressure, etc. So then, at least at this level, almost all the time, we would take a little bit of a departure once in a while, but almost all the time, we would take this K to be a constant, temperature independent, time independent, space independent, right? Now, this invariably would be served to you on a platter. It's a documented property It's a documented thermal property of materials, and it's obtained out of lab experiments and would be served to you in a typical heat transfer problem, right? And it's not too difficult to obtain this. When it comes to space applications, then of course K would have to be modeled, because then variation of K with temperature would have to be taken into account. Reason being that the error that it's going to produce will significantly affect the application it's intended to address, right? Therefore, but for regular applications, the error that would be obtained by taking K to be temperature independent would be so small that it's not going to affect the application that we are addressing. But in space applications and more sophisticated applications, we would have to actually model K as a function of temperature and other related factors and deal with a more sophisticated heat transfer problem. But nevertheless, at this level, it would suffice to know that at a given cross-section, the heat flux, that means watts per meter squared associated with that cross-section, is going to be minus K at that section into the temperature gradient at that section, let's say for heat flowing in the positive direction of the x-axis, right? Now, once we understand this, can I wipe this off? Is this all right? So, right? Now, let me take the heat transfer issue in a little more general fashion, right? One-dimensional, still one-dimensional, but a little more general from energy considerations, right? This Q heat flux, however, let me tell you, reiterate and reassure that in general it's going to be a function of x. This heat flux, watts per meter square, will be a function of x, the direction in which heat is flowing. That's in a very general sense, so to say. And when conditions are not steady, it will not only depend on x. At a given x, it will also depend on time. That's the transient state heat transfer problem, right? Now, let's say heat is flowing in a material medium in the positive x direction, say. This is a cross section of area A, and there is heat flowing perpendicular to this area. Let's say this cross section is located at x. This is the positive direction of the x-axis, and this cross section, let's say, has thickness dx. Let's say this cross section has thickness dx, right? There are two faces to this cross section, one at x, the other one at x plus dx. These are the two faces of this cross section perpendicular to the x-axis, heat flowing in the positive direction of the x-axis, right? Now, I'm not even claiming that the area is the same both at x and x plus dx. Both at x and x plus dx, I'm not even claiming that the area is the same. The area in general could be different. Q could be different, A could be different. So one thing, Q into A will give me watts. That means the power associated or the heat flowing per unit time through that cross section, right? So then, let's say this is A into Q, which is the heat flowing. That means watts entering the cross section. This is watts that enter the cross section. A at that cross section into Q at that cross section, which is AQ at X, That means these many watts are entering the cross section. These many joules per second entering the cross section, right? Now, let's say what leaves the cross section is what leaves at x plus dx. Let's say at x plus dx, the value of A into Q is A into Q at x plus dx. At x plus dx, yes or no? Right? So this is the heat that enters in watts, and this is the heat that leaves in watts through this cross section of thickness dx. Now, again, to present semblance of generality, To just add one more thing to the heat transfer equation, there are materials that could be designed in which there could be an internal generation of heat. There could be an internal generation of heat. First, there could be some chemical reaction going on inside this cross section of thickness dx, or something could be happening, some mechanism that could be internally generating heat, right? And let's say there is G0 watts per cubic meter per unit volume. These many watts per unit volume is the heat internally generated at any given cross section, let's say. This is heat generated per unit volume at any given cross section. Heat generated per unit volume at any given cross section. Now, let me write down the energy balance for this. Let me write down the energy balance for this cross section. Energy balance for this cross section. Heat entering is AQ at x. Heat leaving is AQ at x plus delta x. AQ at x plus delta x. Now, the volume of this I can approximate to A into dx is the volume of this. A into dx. Volume into density. That's the mass of this. Or rather, I just need the volume of this. So, A into dx is the volume of this cross section. The heat generated would be A0 into dx into G0. That would be the watts generated inside this thickness. This into G0, because G0 is internal energy generation. Internal energy generation per unit volume. Per unit volume. So, in A into dx, the heat generated would be A into dx into G0. Right? These many watts would be generated because of an internal mechanism, an internal process going on. Right? Now, this is it. Heat coming in, heat leaving. This is this one. Yeah. See, this G0, let's say in certain materials, this could be the watts or the heat generated per unit time, per unit volume of the material. Right? So then, what's the volume of this? A into dx is the volume of this. Almost now okay. See, if dx is very small, do you realize that the change in area would be negligible? Because it's dx. If I had taken this as delta x, it would have been another issue. But this thickness is dx. This thickness is dx. So because you know the variation is continuous. So over that small change dx, the change in area can't be abrupt, right? So A into dx into G0. Do you realize this is the net heat accumulating in this mass? Yes. This is the net heat accumulating in this mass. What does it do to this mass? It raises the temperature of this mass. So then, this must do the following. These many watts accumulating in the mass, these many joules accumulating every second in this thickness, that must be mass of this, which is A into dx into rho. Rho is the density of the material. Rho is the density of the material, right? A into dx into rho, that's a mass, into, let's say, S is the specific heat of the material of which this is made of, right? S is the specific heat, and into rate at which temperature changes with time. Rate at which temperature changes with time. T is the temperature at x. T is the temperature at x. So then, this is the volume, this is the heat that is accumulating every second. These many watts, where does it go? It goes towards increase of temperature of this thickness, right? Now, what we could do is x plus dx. Let me divide by dx. Then this would be negative of the change in AQ. This is the negative of the change in AQ divided by dx, right? If I divide by dx, then this would give me minus ddx of AQ, isn't it? Will I not get this? AQ is a function of x. This is AQ at x plus dx minus AQ at x, minus taken out. So this is, and if I divide by dx, it will become minus ddx of AQ. It will become minus ddx of AQ if I divide by dx, right? Plus A into G naught is A rho S into dt dt. A rho S into dt dt. Yes or no? Now, to further add to this, let me divide by A. So I get minus 1 by A ddx of AQ. If I divide further by A plus G naught equals rho into specific heat into rate at which temperature changes with time at x, into rate at which temperature changes with time at x. Actually, to be very strict about things, this should have been dou T of T, because T is a function of both x and T. T, temperature, is a function of x and T. But what we are looking at is rate of change of T at this x with time. So it should have been written as partial derivative of temperature with time. That is how strictly I should have mentioned the whole thing, right? But then it's all right. If you understand what I'm implying, that's okay. Now, this Q, the heat flux at any given x, can be written as minus K dt dx. Didn't I tell you? The heat flux, the watts per meter squared, the watts per meter squared at any given x can be written as minus K dt dx. Right? So I write this K as minus dt dx. This then, in a certain sense, at least for this level, is the generalized one-dimensional heat flow equation. One-dimensional heat flow equation for conduction, right? Now, to simplify matters, under steady state, what would happen? This will become 0 because temperature would become time independent. So, partial derivative of T with respect to small t would be 0 under steady state conditions, right? So, when the conditions are steady, what happens? T becomes time independent. And then the rate of change of T with small t will become 0. Right? So the right hand side would vanish. Right? It becomes 0. And then, in this case, I have not assumed that area of cross section is necessarily a constant, because this A is factored inside the derivative, right? So, again, to be more general, this is 1 by A. I could have, as a special case, taken A constant area of cross section in the direction of heat flow. Then this A will come out, this K will also come out, this A will come out, this K will also come out, this A will cancel this A if it's a constant cross sectional area, and this K will come out, leading us to, as a special case, if A is constant and thermal conductivity K is also constant. However, one thing that you want to know here is that this equation will be true when K varies, because K can be written as a function of x. K could have been written as a function of x. K could have been written as a function of x. A could have been written as a function of x. And this would be very general. But now special cases of this, when K is a constant, A is a constant, this A would cancel this A, and then we have K times dt2 dx2 plus g naught is 0, right hand side would become 0. Right? Right hand side would become 0. This would give me d2t dx2 equals minus g naught by k. G naught is an internal heat generation function, right? If I integrate once, then I get dt dx. If I integrate once, I get dt dx equals minus g naught by k into x plus a constant of integration. What? Q is minus k dt dx. That's why this minus sign. So dt dx is minus g naught by k x plus c1, right? So I get the temperature gradient as a function of x. That means the temperature gradient is a linear function of x. It's a linear function of x. However, if there was no internal heat generation, then dt dx would have been a constant. That means the rate of change of temperature with x would be would be x independent, would have been a constant if there was no internal heat generation. That means the temperature gradient would have been the same for all x. Temperature gradient would have been the same for all x if there was no internal heat generation. Right? Now, I integrate one more time. I get t equal to minus g naught by 2k x squared plus c1x plus c2. That's temperature as a function of x, which is a quadratic. So it's parabolic variation. T as a function of x. It's a parabolic variation, yes or no? Right? Now, how do these constants? Yes, you have a question. See, again, if there is physically, in the sense, if there is no temperature, if there is no internal heat generation, what really happens is, I can tell you when would it not be parabolic? When would it just be a straight line? In the sense, if I had q equal to minus k dt dx, suppose, right? And there was no internal heat generation, then the q dot, that means watts, q dot is watts, would have been minus ka dt dx. If there was no internal heat generation and under steady state conditions, these would have been the watts flowing through any cross section of area A in the direction of the x-axis. Now realize that if conditions are steady state, then q dot at any x would be a constant. That means then dt dx would have been a constant, right? Then dt dx would have been a constant. So the temperature over a change of x, no matter where you take that change, the same change of temperature would take place, right? So no, I don't see reason. Essentially it's because of this factor that temperature is varying with x, but faster now. Do you realize that? It's realized that coefficient of x square is negative. Let me be done with that. I'll address that issue in the later part of the class. I'll address that issue also, right? So this is how temperature varies with x. Which is a parabolic variation. Now, how does one obtain these constants C1 and C2? How does one obtain these constants C1 and C2? Well, boundary conditions. Boundary conditions in the sense, let's say they would tell you for example, if the heat flow is taking place between these two limits, x equal to a to x equal to b, say, from x equal to a to x equal to b, if the heat flow is taking place, then they might tell you that the temperature at A, I mean, this could have been, for example, placed in a steam chamber. This could have been placed in a steam chamber, for example. Right? Which means the end A, x equal to A, is always maintained at 100 degrees centigrade. That means T at x equal to A would be 100 degrees. And then they could say that this end is maintained with ice. That means the temperature at B would always be 0 degrees centigrade. Now using these two conditions, you can obtain C1 and C2. This is one possible set of boundary conditions that could be deployed. The other possibilities, there could be many variations around these boundary conditions. This, for example, is one which would help you obtain the constant C1 and C2. Now, I'm saying the way you obtained temperature as a function of x was minus g naught by 2k x squared plus c1x plus c2, right? These are two constants that we need to obtain, and therefore we need two boundary conditions to be able to obtain C1 and C2, isn't it? I'm saying this is one kind of boundary condition that's possible. You know, this end placed in a steam chamber. So the temperature at x equal to A will always be 100 degrees. That means put x equal to A, then T would be 100, right? And this end might have been maintained in an ice chamber. So this end would always be at 0 degrees. So put x equal to B, T will be 0, and you can obtain the constant C1 and C2, right? Now, the other way, see, there are a host of boundary conditions that are possible. I'll just give you some of them. You know, this could be an end which is lagged, means insulated. This could be an end which is lagged. For example, let's say this is x equal to 0 and it's insulated. This is insulated. Now, if it's insulated, the heat flux associated with x equal to 0 must be 0. That means the heat flux at x equal to 0 will be actually the value of minus k dt dx at x equal to 0. And that will be 0. So this is another kind of boundary condition possible. This is another kind of boundary condition possible, right? The third kind of boundary condition possible is, they can say, for example, by some indirect means, they might have determined, and they find that, well, the heat flow rate through this cross section, the heat flow rate or the heat flux, let's say, through this cross section is 4,000 watts. Let's say it's 4,000 watts. Then you can conclude that the, say, watts per meter squared. Then you can conclude that minus k dt dx at x equal to L, let's say this is x equal to L, is 4,000 watts per meter squared. 4,000 watts per meter squared. Let's say that's the heat flux. That's a heat flux at x equal to L. The value of this expression at x equal to L is 4,000. So that can give you another boundary condition, right? So in a certain sense, you know, we have a combination of these boundary conditions coming our way. In almost all of these cases, we will assume that heat is flowing only in this direction, because we would end up, this is like a lateral surface. If I say heat is flowing in this direction and not flowing like this, it really means, or it's equivalent to saying that this surface, the lateral surface, is lagged or insulated. If it's lagged or insulated, means there can be no heat current in this direction. There can be no heat flow in a lateral direction. If, however, I had not lagged that, if I had not lagged or insulated the surroundings, then temperature will not just be a function of x, it will also be a function of y. Then it's going to become a two-dimensional heat problem. That's when it's going to become a two-dimensional heat problem. Now,
find out the equation for x, then with y.
no, you can't superimpose that way. No, you can't superimpose that. I mean, in that case, see, because it's not linear, isn't it? Do you realize that the expressions are not linear? So you can't superimpose. So you could superimpose if they were linear, right? So you can't superimpose stuff like that in the sense. You will assume heat flowing in one direction and not in the other direction, and then in the other direction and not in this direction, and you add them up. You can't do that, right? Now, let me look at the simplest form of the heat transfer or the heat conduction problem. The heat conduction problem, the simplest form of the heat conduction problem. The simplest form would be when you have, let's say, a uniform cross-sectional area, heat flowing through a uniform cross-section. This cross-section at any given x is A. Heat flowing perpendicular to A. Heat flowing perpendicular to A. Uniform cross-section A, K equal to a constant, the thermal conductivity a constant, and no internal heat generation, G naught is 0. No internal heat generation, that is G naught is 0. That's the simplest version of a conduction problem. One dimensional, heat flowing in one direction, so temperature would be a function of x alone. No internal heat generation, steady state conditions, area of cross section is a constant, K is a constant. That's the simplest form of the heat transfer problem. Now, let's say by some means we maintain this end at temperature T1, and let's say we maintain this end at temperature T2 by some means. And like I said, there could be means of doing this. We could certainly do that if we like. Now, so then temperature would vary with x. Temperature would vary with x. Under steady state conditions, temperature would be a function of x alone. Temperature would be a function of x alone. At x equal to 0, it's T1. At x equal to L, it's T2. Through any given cross section, what's the heat flux? The heat flux would be minus K dt dx. That's the watts per meter squared flowing through this cross section. Means the watts that will flow through this cross section would be minus Ka dt dx, would be the watts flowing through this cross section, and that's written as Q dot. Q dot. Right? Now, this watts or Q dot we will also refer to as a heat current. A heat current. We'll also sometimes call it the heat current. We'll also call it the heat current. Now, under steady state conditions, do you realize that the watts that enter a cross section would be the watts that would leave the cross section? With any given cross section, the watts will be the same. The joules per second will be the same across any given cross section because it's steady state conditions. If that was not the case, then the temperature of that cross section would be time independent, So under steady state conditions, Q dot must be the same for any given cross section if G naught is 0. Right? So we are talking of steady state heat conditions, so Q dot is a constant. Now, if Q dot is a constant, What does it mean? It means dt dx is a constant. That means constant gradient. If q dot is a constant under steady state conditions, then it would mean that the temperature gradient is a constant. When would temperature gradient be a constant? If T varies linearly with x, in this case, since the heat is flowing in this direction, temperature is decreasing with x. So then the variation of temperature with x would be like this. This is how temperature would vary with x. T1 here and T2 there. T1 here and T2 there. The slope of this line will give me dt dx, which is a negative number. The slope of this line will be dt dx, which is a negative number. So this is how it varies. This is how it varies. Now, what we could then imagine is that the dt dx for this, is what? What's the slope of this? T2 minus T1 by L, isn't it? T2 minus T1 by L, which is a negative number. That's the slope of this, right? So then, which really means that Q dot is minus Ka T2 minus T1 by L. T2 minus T1 by L, right? So this I can write as, say, T1 minus T2, which means the fall of temperature divided by L by AK. Clear? Now, the reason we would call it the heat current is that this is because of this. Heat has flowed because T1 is greater than T2. That promotes flow of heat from left to right, right? So this is synonymous with potential difference. If this is synonymous with potential difference, we can call it the heat current. Then we could call this the thermal resistance. So this is like the heat current. This is like the thermal potential difference in a certain sense. But this is like the thermal potential difference. This is like the thermal resistance. This is like the thermal current. This is like delta T divided by L by AK. So for a rectangular cross section or for a constant cross section A, heat flowing perpendicular to a constant cross section A over a length L, the thermal resistance is going to be L by AK. The thermal resistance is going to be L by AK. So this is delta T divided by L by AK. Delta T divided by L by AK. That's the heat current. That's the heat current associated with it. Clear? Now, so heat current, delta T is like the potential difference divided by the heat resistance L by AK. Now, suppose you had the following. Can I wipe this off? So for a uniform cross section A, the thermal resistance is going to be L by AK. And if you knew the thermal resistance, this will be the potential difference divided by the thermal resistance, you will get the heat current. Okay. Suppose we had two slabs or three slabs connected like this. Say there were three slabs, slab 1, slab 2 and slab 3. And in general of different thermal conductivity, say this was K1, this was K2 and this was K3. And the lateral surfaces were lagged so that it remains a one-dimensional heat transfer problem. Say this was T initial and say this was T final. And let's say the area of cross section of each of these slabs was the same. And say this is the interface between 1 and 2. Let's say it has temperature T2. This is the interface between 2 and 3 and let's say it has temperature T3. Then realize that the heat current in this slab will be the same as the heat current in this slab will be the same as heat current in. That means Q dot is the same for all the slabs, right? So Q dot, then the heat current with each of the slabs. For this, what's the potential difference? Ti minus T2. What's the, let's say if A was the area of cross section of this, then what would be the thermal resistance of this? Let's say if this was L1 and say this was L2 and this was L3. Then what would be the thermal resistance of this? L1 by AK1. Now, that means be the heat current through this, right? So, which is like T2 minus T3 divided by L2 by AK2. Thermal resistance of that, and that must be the heat current through this, which is like T3 minus TF divided by L3 by AK3. Which is the same as sum of the numerators divided by sum of the denominators. Suppose I didn't want to deal with the interface temperatures T2 and T3. Suppose I was only interested in Ti and Tf. One single slab with n points at temperatures Ti and Tf and of length L1 plus L2 plus L3. Then each of these could have been written as sum of the numerators divided by sum of the denominators, which is like Ti minus Tf. That's the total potential difference across the composite slab. That's the total potential difference across the composite slab divided by this plus this plus this sum of the thermal resistances. So which is like L1 by AK1 plus L2 by AK2 plus L3 by AK3. So then can I say that the total thermal resistance would be R1 plus R2 plus R3. So these are three thermal resistances in series. These are three thermal resistances in series of thermal resistances L1 by AK1, L2 by AK2 and L3 by AK3. Thermal resistances in series. Clear? And this is the heat current associated with it. In fact, to tell you more realistically, this is a very ideal problem. In real life, we have situations which are a lot more involved in heat transfer. Realistically, for example, when you look at the contact 1 and 2, just look at this contact 1 and 2. In fact, there would always be a certain gap. It can't be airtight. There would always be a certain gap here. This would be, let's say, like an air gap. And this would also offer thermal resistance. This essentially will also offer thermal resistance. That means across this air gap, which you can't see. When you're imagining that it's perfectly pressed. But realistically, it could be an air gap, for example. Or maybe it could be an adhesive gap. There could be an adhesive which might show up as a small thickness, right? So then, that by itself will offer thermal resistance. And if that offers thermal resistance, then at the interface, the temperature would, So there is a contact resistance. There is a contact resistance also in real life situations that we have to deal with. And if if the problem is a sophisticated issue that we are dealing with, then we will have to also model the contact resistance, if any, whenever two slabs are joined end to end. So we will have to account for that in a real life situation, the contact resistance. Now, so these were resistances in series, and that's how you deal with them, right? Now, you could have had say a slab like this of length L, of area of cross section A1 and thermal conductivity K1. Another slab of the same length, say, of area of cross section A2, thermal conductivity K2. A third slab A3, thermal conductivity K3. Temperature of this surface, say T1, temperature of this surface, say T2. These are the temperatures of the two surfaces. Now, there is a heat current Q dot. These many watts are entering this face, out of which there is Q1 dot associated with area of cross section A1, Q2 dot, these many watts associated with A2, and these many watts associated with A3. Then, obviously, Q dot must be Q1 dot plus Q2 dot plus Q3 dot. So, the total heat current Q1 dot, which is the difference in temperature delta T divided by 1 by the thermal resistance L by A1 K1 plus the temperature difference, same temperature difference, 1 by L by A2 K2 for this plus 1 by L by A3 K3 for this. Yes or no? Which is the same as, effectively speaking, delta T, if there was one single unit, divided by the equivalent thermal resistance, is the same as delta T divided by the equivalent thermal resistance Req, right? Then can I say that 1 by Req must be 1 by R1 plus 1 by R2 plus 1 by R3? So these are resistors, thermal resistors in parallel. So we can apply the series parallel stuff exactly the same way that we applied in current electricity, isn't it? Right? And we could have had series parallel combination also. We could have had series parallel combination also. I'll tell you how, for example. Can I wipe this off and proceed further? And all of this, by the way, only in steady state conditions, right? Say, there are a number of rods of length L. Infinity of such cells, right? These are various rods, length L, and let's say thermal conductivity K for each, and let's say area of cross section A for each. each of the rods, right? These are various rods. Infinite ladder. This is like an infinite thermal ladder. I'm producing an infinite thermal ladder. Between points A and B, between points A and B, A maintained at temperature T1 and B maintained at temperature T2. Infinite thermal ladder. Between A and B that are maintained at, say, temperature T1 and I want to find the heat current of this, the heat current that enters A and the heat current that leaves B. Right? Naturally, say there is Q dot that enters A, it gets distributed here like normal current does, goes there, comes here, combines, and so on and so forth, like current would normally. And then eventually it would recombine, it will then come back to B, and so on and so forth. Right? So Q dot that enters A is Q dot that leaves B, for example. And I want to find I want to be able to find the heat current that enters A or leaves B. The heat current, total heat current associated with this ladder. Now, essentially what I then want to do is, across A and B, I want to find the thermal resistance. Across A and B, I want to find the thermal resistance across A and B, right? Let me assume it's R. Okay. So then, and each one of these ladders will have thermal resistance L by AK. The thermal resistance of each of the ladder, each of the constituent elements, rod, would be L by AK. So this is R1, this is R1. Now, if across these two it's R, then if I look at whatever is to the right of this, then this whole thing could be replaced by R, isn't it? Right? So then there is a R, and then this is R1, this is R1. That's the equivalent thermal circuit. That's the equivalent thermal circuit between A and B, isn't it? Now, the equivalent of all of this across A and B must be R. That's what we have taken this, right? That means R1, R and R1 in series, in parallel with R1 will give me R, isn't it? Now, so which means 1 by 2R1 plus R, 2R1 plus R plus 1 by R1 must be equal to 1 by R, the equivalent thermal resistance of the ladder across A and B. Clear? When you cross multiply and solve, you will be able to solve for R in terms of R1. R1 you already know. You can solve for R in terms of R1, you will get a positive R and a negative R. You take the positive R. So you would know R, the equivalent thermal resistance of this network across A and B, where the potential difference applied across A and B is T1 minus T2. So then the heat current would be T1 minus T2 delta T divided by the thermal resistance R across the network. So this will give me the heat current entering A and leaving B, right? So the same set of principles that you have learnt in current electricity will apply here. Instead of potential differences, you will have temperature differences. Instead of electrical currents, you will have thermal currents. Instead of electrical resistances, you will have thermal resistance. So you have an analogy in front of you, right? Not that it would be required, but if you wanted, you could apply star delta, you could apply Thevenin, and so on and so forth, right? All sort of things could be done. Although at this level, they would not give you anything that would require that, but for your consumption, for your mental solace, you might understand that the same set of principles, you can apply the junction rule. You can apply the junction rule very effectively. The algebraic sum of the currents entering a junction will be 0, right? Which means, let's say, if there is a rod here, this end is maintained at 25 degrees centigrade. Say this is length L1, area A1, thermal conductivity K1. This is another rod, length L2, area of cross section A2, thermal conductivity K2. The third rod, length L3, area of cross section A3, thermal conductivity K3. Suppose this is 25, or let me just get very general. Say this is temperature T1, this is temperature T2, this is temperature T3, say. And I want to find the junction temperature of this. I want to find the junction temperature of this under steady state conditions. That means the algebraic heat current entering T must be 0. So heat current here is going to be T1 minus T divided by the thermal resistance of this. That would be the heat current in this direction, which would be L1 by A1 K1, right? Plus the heat current in this direction, algebraic heat current. So it could be positive or negative, right? So T2 minus T divided by L2 by A2K2 thermal resistance of this, plus the heat current in this direction, algebraic again, T3 minus T divided by L3 by A3K3. This must be 0. And this will enable you calculate the junction temperature. So the junction rule applies very effectively, very easily, right? You can apply KVL, KCL, everything that you like, right? Right? Now, let me look at cases where one-dimensional, steady state, but say the area of cross-section could be varying, Say there is a cylindrical rod of inner radius small a, outer radius small b. Inner radius small a, outer radius small b. Right? Length L, thermal conductivity K. Length of the cylinder going into the plane of the board. Now, I'll not talk of a situation where heat is flowing longitudinally. If heat was flowing longitudinally, then very clearly the thermal resistance of this, see, if it was flowing longitudinally, it would have been L divided by area of cross section pi b squared minus a squared K, right? If it was flowing longitudinally, right? We are now not talking of a longitudinal flow of heat. We are talking of a radial flow of heat. Heat flow in the radial direction. Radial flow of heat. Heat flowing like this. Radial flow of heat. That's radial flow of heat, right? Now, once again, radial or longitudinal. The watts, see, the area of cross section in this case is varying, isn't it? It's not constant, the area of cross section is varying. If you look at a radial flow of heat, then the area over which heat is flowing, see, it's flowing through cylindrical surfaces, it's flowing out of cylindrical surfaces whose curved area will vary with as you move away from the center. For example, at a given instant of time, if this was A, this was B, If you really think about it, this is radius r and this is thickness dr. Radius r and this is thickness dr. Do you realize when heat is flowing through this, then it's flowing through a curved surface of area 2 pi rl. 2 pi rl is the curved surface area over which heat is flowing, and r is changing. So the area of the curved surface is changing with time, right? So it's variable A. Variable A. You know what I'm saying? Or are you lost? No? Lost? So heat flowing radially outwards in which area of cross section is varying. Area of cross section is varying. But the cardinality is not lost. The cardinality is that the heat current through any given cross section must be the same. And since, because of symmetry, heat is flowing only radially outwards, temperature would be a function of R alone. Temperature would be a function of R alone. Do you realize that? So in that context, a one-dimensional problem, because it depends only on the radius of the cross section. That means if you take at a distance R a curved surface area, a cylindrical area, then at all points on this surface the temperature would be the same, right? I now want to be able to find the thermal resistance of such a unit, a cylindrical unit in which heat is flowing radially outwards. If it was flowing longitudinally, then the thermal resistance would be L divided by pi b squared minus a squared k. But if it's flowing out, A is not constant, so I can't say L by a k because A is varying. So then, let's say if this was at temperature T1 and this was at temperature T2, and let's say heat was flowing radially outwards, then at any given R, let's say at any given R, what would be the heat current associated with that R? The heat current associated with any given R, Q dot, that means watts. Q dot is like dq dt. It's like dq dt, right? Watts. Would be minus k times the area of this, which is 2 pi rl, which is 2 pi rl. That's the curved surface over which the current wavefront lies, right? And you can also associate cylindrical wavefronts with this. As the current is passing radially outwards, you can imagine this to be cylindrical wavefronts, right? So 2 pi rl, L is the length of the cylinder, Ka, and then the temperature gradient at R would be dt dr. The temperature gradient at R would be dt dr, Ka, dt dr. Yes or no? Now, can I say Q dot into dr by R is minus 2 pi kl dt? Minus 2 pi kl dt dr by R. Now let me integrate both sides. Interesting, when I integrate both sides, can I take this Q dot out of the integral sign? Yes, because Q dot is the same for all R. The heat current, watts entering a given cross section will be the watts that will leave the cross section and will enter another cross section. So the watts associated with all the cross sections is going to be the same, right? So I could scoop Q dot out and then I integrate this and then I integrate this. 2 pi kl, again, if I like, I could have taken k a function of temperature also, right? Or if k is given to be a function of R, what I would have done is I would have combined that k here. So in this, right here, I still have left my options open to vary k with R or to vary k with temperature if I choose to. You know what I'm saying? If k is a function of R, what I would have done is say k, someone says, is CR cubed. Then that's, if that's it, then it's not a one-dimensional problem. It's not a one-dimensional problem. Yes, but you're right. You know, but the other thing that would happen is, I'll tell you, if it's both, then it's only implicit in the sense that if T is a function of, if this T, this K is a function of temperature and R, then essentially that T by itself will be a function of R. So it could eventually be reduced to a function of R alone, isn't it? Although the whole thing might look a little implicit. We might not be able to separate the variable because we are only basing it on the premise that we know how it's exactly varying. But if we could separate them, then T would be a function of R alone, because this K would be a function of R alone because T by itself is a function of R, right? So to simplify matters, someone would have to tell you how K is varying, whether it's varying with R. If it's varying with R, this is how it's varying, right? And you could combine that K with this R while you are integrating, and you can deal with a little more sophisticated heat transfer problem, in which K is not a constant but also varying, right? And then if it's a constant, then wonderfully simple, good for us. While R varies from A to B, inner radius to outer radius, T varies from, let's say, T1 to T2. Which means so this is all radial heat flow in a cylindrical rod. Radial heat flow in a cylindrical rod. So then I get Q dot into log B by A. That's the left hand side. Equals minus 2 pi K, or I could say 2 pi KL into T1 minus T2. Or Q dot is delta T, that's a potential difference, divided by 1 by 2 pi KL log B by A. Yes or no? So which means for a radial flow, radial cylindrical flow, the thermal resistance is going to be 1 by 2 pi KL log B by A, log B by A. 1 by 2 pi KL log B by A, that's the thermal resistance for a cylindrical flow. Does it make sense to all of you? Now, we could have had, in a similar manner, a spherical flow, a spherical conductor, right? We could have had a spherical flow of heat. So you might want to remember this. For radial flow, however, don't get mixed up. Don't get mixed up. If it's a longitudinal flow of heat, then L by AK, because A is a constant, which is the cross-sectional area, K is a constant, right? That's for a longitudinal flow, it will be like a slab. But if it's a radial flow, where the area is varying because the heat fronts lie on cylinders of varying cross-sectional area, right? Then it's going to be this 1 by 2 pi KL log B by A. That's going to be the thermal resistance. Now, for a spherical flow, spherical radial flow, again spherical radial flow. A sphere, let's say the inner surface maintained at temperature T1, the outer surface maintained at temperature T2. Concentric spheres, right? And K is the thermal conductivity. During the flow, the heat current will pass through a sphere of radius R, will pass through a sphere of radius R. I am talking of a radial flow of heat. So it will pass through a sphere of radius R, right? And let's say Q dot is the heat current associated with it. Let's say Q dot is the heat current associated with it. Q dot is the heat current associated with it. then can I say that Q dot would be minus K. What would be the area through which it's going to be flowing? 4 pi r square, 4 pi r square. And T would be a function of R in this case, and the temperature gradient at R is going to be dT dr, dT dr. Does it make sense to you? Again, Q dot into dr by r squared is minus 4 pi k dt. Right? Q dot is the same under steady state conditions, so it will come out of the integral sign. This R varies from A to B, T varies from T1 to T2. So that gives me Q dot minus 1 by R, right? So this will give me 1 by A minus 1 by B equals 4 pi K T1 minus T2. So that's delta T. That's delta T. So then I get Q dot, the heat current, as delta T divided by 1 by 4 pi K 1 by A minus 1 by B. So what's the thermal resistance associated with that? Thermal resistance is going to be, for a sphere, the thermal resistance is going to be 1 by 4 pi K 1 by A minus 1 by B. Right? Okay. Refer to the sheet 1. Let's look at problem 1. Two thermally insulated vessels, each containing n moles of an ideal monoatomic gas, are interconnected by a rod of length L. An area of cross section A and a thermal conductivity K. And the lateral surface is lagged of this. All that it means is there would be no lateral flow of heat. It's going to be a one-dimensional flow of heat if the lateral surface is lagged. If at time t equal to 0, the temperature in this is T1 and the temperature in this is T2 at time t equal to 0. T1 greater than T2, T1 greater than T2. Neglecting thermal capacity of the rod, calculate the temperature difference between the gas temperatures as a function of time. Now the temperature difference would decrease. The temperature difference would decrease at time t equal to 0. Let's say the temperature difference was 0. At an instant of time t, we want to be able to find the temperature difference theta. Theta is the instantaneous temperature difference. Oh, sorry. T1 minus T2. The initial temperature difference is T1 minus T2. We want to be able to find the temperature difference at an instant of time t. Now, say at a certain instant of time, the temperature difference across the ends of this is theta. Theta means this temperature minus this temperature. Then, what would be dq dt at this instant. That means the watts flowing through the rod at this instant, that's going to be Ka into theta by L. Ka into temperature difference theta divided by L, that's going to be the watts associated with the rod, right? Which means in a small time dt, the heat flowing from here to there, the heat flowing dq from here to there, that means the heat lost by this dq, it must be the heat gained by this dq. That's equal to Ka theta divided by L into dt, right? Which means the temperature of this decreases, temperature in a small time dt decreases by an amount. See, it's losing an amount dq, right? Decreases by what amount? dq divided by ncv. Tell me. Because the heat is at the expense of internal energy. It's at the expense of internal energy. Cv for a monoatomic gas is 3R by 2. 3R by 2. Gamma is 5 by 3. Gamma is 5 by 3. Cv is 3R by 2. Cp is 5R by 2. Right? So the decrease in temperature of this is dq by ncv in a small time dt. The increase in temperature of this, because this has gained dq, increase in temperature of this is going to be dq by ncv. Yes or no? Right? Now, if the temperature of this decreases, the temperature of this increases, the temperature difference will decrease. The temperature difference will decrease by an amount this plus this. Yes or no? If the temperature of this decreases by 1 degree, the temperature of this increases by 1 degree, then the temperature difference will decrease by 2 degrees. Yes or no? Right? So the temperature difference decreases by an amount 2 dq by ncv. Right? Theta is decreasing with time. Theta is decreasing with time. So, do you realize that this is actually minus d theta? The decrease in temperature difference, then would be minus d theta. Right? D theta will be negative. D theta will be negative because temperature theta is decreasing with time. So, d theta would be negative. So, this, right? What are we seeking to find? We are seeking to find theta as a function of time. What we could do then is we could write dq as this. We could write dq as this. Minus d theta is 2 Ka theta by L Cv. Cv is 3R by 2. So by 4. Cv, replacing the Cv by into N. Yes or no? This theta I can bring in here. Right? Writing Cv as 3R by 2. This is what transpires. Integrate both sides. At time t equal to 0, what was theta? T1 minus. At time t equal to t, let's say the temperature difference becomes theta. Log theta by t1 minus t2. You will know theta as a function. All of this will come out of the integral sign. This will simply be t. So this will become 4 Ka by 3 NLR into t. And you would know theta as a function of time. Temperature difference as a function of time. Do you realize that? Let me illustrate a little more. 2 I solved, you know, this network I solved for you, the infinite ladder of thermal resistors. A highly conducting solid cylinder. By the way, can you list out the assumptions that I made in that problem, the one that I just solved for you? You know, there was this. At least tell me one very relevant assumption that I made. This was n moles. This was n moles. Can you? Okay, that's fine. Yes, the containers are insulated. That's fine. What else? There's another assumption that you didn't poke me with. See? Most important assumption with which you could have poked me was, well, you know, I assume that at all times the temperature of this remains uniform. The temperature of this remains uniform. You know, there is conduction occurring here. Very realistically speaking, there would be a temperature profile in this volume. There would be a temperature profile in this volume. I mean, if the temperature of this becomes 4 degrees, then at that very instant the temperature of this becoming 4 degrees is unreal. It will take a little while for the temperatures to be in equilibrium, for there to be thermal equilibrium in this container. I've assumed that at all times there is thermal equilibrium instantly taking place, which is not necessarily true, isn't it? I mean, if the temperature of this is varying, then at that very instant the temperature of the other parts of the container will become that. Is not practical to think. It's practical to think, all right, but is not necessarily true. Right? So now this assumption will be, which means when can that happen? That can happen if this is the conductivity of this is infinite, very large conductivity. So any change, any thermal change brought about here at a certain instant is instantly communicated to the rest of the cylinder. That's one case where that could happen, right? Now it's a gas. Would you expect that kind of a thermal conductivity in a gas? No, you can't expect that kind of a thermal conductivity in the gas. So then the other possibility where this assumption, if this was a very tall cylinder, then that assumption would have been gross. Which means this volume must be really, really small. This volume must be really small for this assumption to be legitimate. Do you realize what I'm saying? Right? Now, in real life, however, when we simulate problems, I'll tell you, we have to consider the temperature profile. In real life, heat transfer problem associated with this model would be very, very involved, very involved. I mean, it's not going to be as simple as I communicated to you. It's going to be a lot more complicated. Okay, let's look at problem 3. A highly conducting solid cylinder. Highly conducting solid cylinder of radius A and length L. This is the length L, right? Into the plane of the board. Is surrounded by a coaxial layer of a material, of thermal conductivity K, where the temperature of the surrounding space is T naught. Temperature of the surrounding space is T naught, much higher than the temperature of the cylinder. That's given. If the heat capacity per unit volume of the cylinder is S, the heat capacity per unit volume of the cylinder is S.
Sir, I know this was the earlier problem, sir. Sir, how do you find out the heat profile of a gas?
Why not?
Sir, like gas molecules have a lot of space, intermolecular space in between them. Finding out heat profile is very
You're right. But then, they are not like 1 kilometer long, isn't it? The separation is still, compared to solids, they are larger. Compared to liquids, they are larger, but they are still in angstroms only, isn't it? They still are in angstroms. So, for all practical purposes, you can imagine it to be packed material, isn't it? So, that's fine. It only feels good to imagine that they are far apart and their potential energy is zero. There is no interaction. But then, they still are of the order of angstroms. So, you can imagine it to be almost packed, right? Was that your question? Yeah, okay. Now, the initial temperature of the cylinder is T1. Initial temperature of the cylinder is T1. We want to find the time required to increase the temperature of the cylinder from T1 to T2. There would be heat flow this way, from outside to inside, right? Assume end faces to be thermally insulated. These are the end faces. If the end faces are thermally insulated, it would mean that there is no longitudinal flow, isn't it? These are the end faces, this way, and L units into the plane of the board, there is another end face, right? That's thermally insulated. If the end faces are thermally insulated, there would be no longitudinal flow, isn't it? There would be no longitudinal flow, right? So, the flow is purely radial, is it not? Now, this temperature is growing. At an intermediate instant, let's say the temperature of this is T. By the way, and this radius is B. What's the thermal resistance of this unit? I told you 1 by 2 pi KL, L is the length, log B by A. 1 by 2 pi KL log B by A is the thermal resistance of this. Now, at any given instant of time, then, the heat current associated with this Q dot that's flowing through all cross sections, what's flowing through all cross sections is going to be the potential difference, which is T naught minus T1, divided by the thermal resistance, which is 1 by 2 pi KL log B by A. That's going to be the heat current, right? T naught minus T. T naught minus T. Now, if these many watts are entering this cylinder, what are they doing to the cylinder? Increasing the temperature of the cylinder. Now, one thing. This is heavily conducting. So, if a certain change is brought about on the skin, it's communicated to the bulk. So, at all points of the solid cylinder, the temperature at any given instant will be because it's heavily conducting. Now, that must be equal to the mass into specific heat is thermal capacity. Mass into specific heat is thermal capacity, right? And it's given that the thermal capacity per unit volume of this is S. So, the thermal capacity of volume pi A squared L, that's the volume of this, right? Thermal capacity of this is going to be this into L. So, this will give me like a mass into specific heat. It's given thermal capacity per unit volume is S. So, thermal capacity of volume pi A squared L will be this, yes or no? So, this is like mass into specific heat equivalently, right? Into rate at which temperature changes with time for this. Right? All that you need to do is bring this T naught by T below this dt, integrate. At time t equal to 0, the temperature difference was T naught minus T1, right? At time t equal to T, the temperature difference, or rather T becomes, at time t equal to 0, T is T1, at time T, T becomes T2. So, the limits of integration would be 0 to T, T1 to T2 for the cylinder. And you can find the instant of time T when the temperature will become T2 for the cylinder. Right? Let me illustrate it. Okay, now 4. Look at 4. A solid round cylinder of radius A this is a solid round cylinder of radius A is made of material whose thermal conductivity depends on the distance r. Thermal conductivity depends on the distance r as C into r squared. C is a constant. So, thermal conductivity varying with r, right? Calculate the temperature gradient if rate of flow of heat through the rod is h. Now, one thing, this is not radiant flow of heat. This is longitudinal flow of heat, but in any given cross section, the flow of heat is still longitudinal, but the thermal conductivity in a given cross section is varying with r. You know, this could be a complex material made whose thermal conductivity is varying in the r. The flow of heat is still longitudinal, right? You know what I'm saying? Now, I want to find the temperature gradient. In this. If H is the heat current associated. So, do you realize that heat is now not flowing over 2 pi RL? It's flowing through this. It's flowing through these rings internally. It's flowing through these rings inside, parallel to the axis of the cylinder, right? Through these rings. So now, through this particular ring that I have selected, right? The heat current dq dot, small amount of heat current associated with this, the flow is longitudinal, is going to be what? Is going to be what? K, which is CR squared, into area is 2 pi r dr, Ka into the temperature gradient, d theta dl, L is along the length of the cylinder, into d theta dl, that's a temperature gradient. D theta, when you go inside, the variation of temperature from this ring to its next parallel ring, that over a distance dl, parallel to the axis, this is this, and of course with a minus sign, minus d theta dl, because theta is decreasing with L, that will give me the temperature gradient, right? Now when I integrate this d theta dl is the temperature gradient, will come out of the integral sign, R varies from 0 to, let's say, A, and sum of all the dq dots, see, in any given cross section, dq dot through this, dq dot through this, that will give me the total heat current through the cross section. Sum of all the dq dots is H, that's it, right? So H is minus d theta dl 2 pi c, this is r cube, so a power 4 by 4, right? So d theta dl or minus d theta dl would be 2h by pi c a power 4. That will give me the temperature gradient. That will give me the temperature gradient. Right? Look at problem 7. Look at problem 7. Spherical refrigerator. Radius R. Heat exit. Surrounded by water at 0 degrees centigrade. And the surface of this maintained at minus theta degree centigrade all the time. The surface of this maintained at minus theta degree centigrade all the time. Find the time in which a layer of ice of thickness R appears on its surface. Find the time in which ice of thickness R appears on the surface. Obviously, what's going to happen here? See, physically understand this. There is of course a compressor here which is maintaining the surface of this at minus theta degree centigrade, right? So you don't have to bother about that mechanism, right? There is a mechanism that takes care of this. Now, when this is maintained at minus theta degree centigrade, the outside is maintained at a higher temperature, 0 degree centigrade. So heat will flow from outside to this. So the extra amount of heat, of course, is thrown out. There is a heat exit through this. But while heat flows from there to here, what would happen? Water at 0 degree centigrade would get converted into ice at 0 degree centigrade. Water at 0 degree centigrade would get converted into ice at 0 degree centigrade, for which it will require latent heat. So what flows through this is latent heat. What flows through this spherical refrigerator is latent heat. Yes or no? Yes. You know? Of what? No, only the area of, see, when there is heat exchange between this and this, it's only the, that's why it's growing, the area of this is growing. Right? What's the thermal resistance of a, so essentially, you know what would happen? Over a period of time, this is initial radius R. After a while, let's say, there is a thickness x minus R. Ice of thickness x minus R develops after a while, let's say. That means now, in this state, this is an intermediate state. When you have thickness x minus R of ice, that has already developed over it. The temperature of this is 0 degrees. The temperature of this is theta degrees. The temperature of this is theta degrees, isn't it? Now, what's the heat flow rate through this in a small time dt? What's the heat flow rate through this? dq dt, dq dot dt, right, is going to be the temperature difference 0 minus, this is minus theta, sorry, this is minus theta. So theta divided by the thermal resistance of the sphere, thermal resistance of the sphere, yes or no? Thermal resistance of the sphere. Now when you have the thermal resistance of the sphere into dt. Now where does this dq dot go? when this amount of heat goes from here to here, yes, where does this heat come from? It comes at the expense of formation of ice. It comes at the expense of formation of ice. So what really happens is, when this dq dot flows in time dt to the inner surface of this, we have a layer of ice of thickness dx. We have a layer of ice of thickness dx that develops. An additional layer dx develops because this dq dot is obtained out of freezing this volume of ice. It's obtained out of freezing this volume of water into ice. Yes or no? In the process, how much of heat is released by this dx? Mass into latent heat. This dq dot must be mass of this into the latent heat of ice to the latent heat, right? So mass of this is what? Well, 4 pi x squared dx is the volume of this into rho. That'll give me the mass into latent heat. That must be dq dot. Right? Now, have I told you the thermal resistance of a spherical unit? Inner radius A, outer radius B. Instead of A you have R, instead of B you have X. Check on the thermal resistance of that. Instead of A you have R, instead of B you have X. 1 by A minus 1 by B. Whose cylinder? That was cylinder. Sphere, you will have 1 by A minus 1 by B. So, you will have like 1 by R minus 1 by X. Plug in that. So, this will be a function of X. This R thermal will be a function of X, which you can bring in here. And integrate this. Yes or no? Replace the R thermal in terms of X. And you have to bring that R thermal here because it's a function of X. It will involve like a 1 by R minus 1 by X. Isn't it? See? 4 pi Rx 1 by, right? So you can bring that right here and integrate this. When X is 0, time is 0. No, I'm sorry, when X is R. Initially X was R, time was 0. When X becomes 2R, the thickness becomes R. Isn't it? The problem asks you the time it takes for the thickness to become R. That means X runs from R to 2R. X runs from R to 2R from time t equal to 0 to time t equal to t. So you will be able to find the time it takes for this to happen. Right? Let me look at 10. So there is water in this unit of thermal capacity. That means mass into specific heat is C. Initially, the temperature of this is also T naught, same as the temperature of the surroundings. And there is a metal cover here of thickness B, thermal conductivity K, which is capable of conducting heat from the inside to the outside. Right? Now, there is this water heater. You know, its rating is given in watts. So, it generates H watts. It generates H watts of energy. When it generates H watts of energy, the temperature of this rises to more than T naught. Right? And when the temperature of this is more than T naught, there would be conduction from here to here. Right? So, the temperature of this will eventually become a function of time. Right? So, we want to find T a function of time. Temperature a function of time. One thing, then, at any given instant, T is the temperature of this. If T is the temperature of this, then what's the heat that is conducted out? How many watts is conducted out at that instant of time? K times area, T minus T naught divided by B. These are the watts that are conducted out. What are the watts that are entering the system? H. So what is the net accumulation of heat? This much conducted out. This is, and what does this do? It increases the temperature of this. So this must be mass into specific heat, which is C into dt. Right? You can bring this below this. You'll get an exponential function. You'll be able to get T a function of time. At time T equal to 0, capital T was T naught. At time T equal to T, it becomes something. You'll be able to obtain T a function of time. Again, the assumption here, we are assuming that this is highly conducting. Alright. And of course, there would be, it's a fluid, there would be convection currents here, which would have a sense of, obliging by bringing about thermal equilibrium from instant to instant, but not good enough. We are assuming that there is very high rate of convection, conduction, everything going on here, and it's maintaining the temperature of this ST. Realistically, there would be a temperature profile inside this also. There would be a temperature profile inside this also. That's a real life problem, right? So that's how you do this. Clear? Not a problem? Okay, now I've given you some basic idea of conduction, especially one that involves steady state and one dimensional, predominantly one dimensional. It's important to understand that there is another mode of heat transfer. See, there is a hot surface. Say this is a hot surface at temperature T hot. Right? At temperature T hot. This is becoming a hot surface, for example, right now. Okay? And there is a fluid flowing over it. Let's say there is a fluid flowing over it. There is fluid that's made to flow over the surface. Then it's found that the temperature of this decreases. It becomes cooler. Temperature of this becomes less. In this case, the molecules that flow over this and that come in contact with this communicate heat. There is transfer of heat and they carry away the heat from the surface. They carry away the heat from the surface. Now, this mode of heat transfer between the fluid and the surface in this case, for example, is because of a bodily flow of one thing, right? There is a flow involved here. There is a bodily flow of molecules somewhere, right? This mode of heat transfer is convection. This mode of heat transfer is convection. It's because of the small contact period that the molecules have with the surface, that they carry away the heat. Now this mode of heat transfer is very complicated, and that's the reason they have chosen to not keep it in your IIT JEE syllabus. The model associated, essentially then, at any given instant of time, say this is the temperature of the fluid flowing over it, Tc is the temperature of the fluid flowing over it, then the watts per meter squared associated with it, the watts per meter squared associated with this is going to be given by some H into Th minus Tc, Th minus Tc at any given instant of time. Tc is the temperature of the fluid flowing over it, and Th is the temperature of the hot surface. Now the problem is, it looks so easy, and why is it not kept in the syllabus, right? The problem is obtaining this value of H. It's the biggest problem in heat transfer. This is called convective heat transfer coefficient. And you know what are the factors that it can depend on? One, the thermal property of the surface and the thermal property of the fluid. That's one thing. The velocity of the fluid, you realize that it will also depend on the velocity of the fluid. And in fact, it will also depend on Th. It will depend on Th as well as Tc. Now, Tc can be assumed to be practically constant. Let's say, there is a huge volume that I'm making to flow, but Th can't be constant, right? This is a huge mass whose temperature does not vary, but this Th will certainly vary, and this H actually will vary with Th. This problem of convective heat transfer is very, very involved, I mean, like I said, it will depend on all the properties of this fluid. Yes, it will depend on the thermal properties as well as other properties of this fluid. Everything. So then, it's really complicated. But to tell you honestly, if at any point of time you have to deal with heat transfer, to imagine that there is only going to be conduction in a given situation is utopian. There is simultaneous presence of conduction and convection for sure. Yes, radiation also, but very rarely would you find a situation in which, there is only conduction. It's only for an exam that we give only conduction. But a real life problem involves convection, it involves conduction, and it involves radiation as well, right? So this model is not dealt with at this level, but then those of you who go on to study, become, core mechanical engineers doing core simulation, a typical heat transfer problem, if you have to model a furnace, it will involve like 1500 differential equations with 1100 boundary conditions and all partial differential equations. They can't be solved with the help of the 6 forms of differential equations that you have learnt at this level, right? The solution to those differential equations are done using either with what's called finite element methods or numerically. They are done numerically, So they are very, very intricate, and for each of those differential equations, you will have to devise a new technique of solving that differential equation. It will not be there in Tata McGraw-Hill books, okay, or Cengage. So in any case, just a passing reference to convection, but we need to know a little bit about radiation. Again, that too, the core radiation, radiative heat transfer is very, very involved, although less involved than convective heat transfer. Yet, some of the approximations that you learn with radiative heat transfer are within the scope, purview and reach of students at this level. So, just to take you very briskly past the rudiments of another mode of heat transfer, which is radiation. Now, both conduction and convection were modes of heat transfer that took place in presence of material media, right? A material medium was required for this mode of heat transfer. However, you'll find, let's say, that if there is this hot surface, TH, right, and in an enclosure, which is a cooled enclosure, temperature Tc, right, and there was vacuum here. There was vacuum here. Now, if there was no material medium between the two, you couldn't have had conduction, you couldn't have had convection. Yet you find that the temperature of this decreases and the temperature of this increases. That means there must have been a third mode of heat transfer which does not require for its propagation a material medium, and that mode of heat transfer is radiation, Now, essentially, there is an ideal radiator. There is an ideal radiator. When we talk of these radiations, these are essentially electromagnetic waves. When I talk of these radiations, thermal radiations, these are electromagnetic waves. So, we'll have all properties of electromagnetic waves, right? Now, however, they can get attenuated. The signals, these thermal waves could lose intensity. If they travel through a material medium, they can lose intensity. There could be a material medium which is not transparent to their propagation. See, vacuum is transparent to propagation of electromagnetic waves. It will not attenuate or dilute electromagnetic signal. But there could be a medium, let's say there is water through which an electromagnetic wave travels, thermal radiation in the form of electromagnetic wave, then water will attenuate and dilute the intensity of the electromagnetic waves, because it's going to absorb some of the electromagnetic waves, and the signals, the thermal signals, will become weaker as they propagate along the line of propagation. Now, there is what's called an ideal radiator if it's at temperature T. When I talk of thermal radiations, we now all of a sudden move not to degree centigrade but to degree Kelvin. We now talk in terms of degree Kelvin, and if there is this surface at temperature T, then it's an ideal surface if the watts per meter squared, the Q, that is the watts per meter squared that it radiates, we'll call it E, let me call it E, is some constant sigma into the fourth power of the temperature. This is the radiation model for an ideal surface, where the watts per meter squared is proportional to the fourth power of the absolute temperature, and this sigma is a constant and is called Stefan-Boltzmann constant. And is a value 5.67 into 10 to the power minus 8 watts per meter squared, degree Kelvin to power 4, watts per meter squared per degree Kelvin to power 4. That's Stefan-Boltzmann constant, and this is called Stefan's law. In fact, it's Stefan-Boltzmann law. Stefan does not matter. Sit down. Now, to tell you again, this is very, very involved. I mean, this they have obtained by experiment. Not only by experiment, the check was with experiment, but in this case, it was not purely empirical. There is a proof which is like very huge proof of this. We can't spend time on this, but if you like, I can give you material which you can read and get. But it's very involved proof of this. It's a very involved proof of this. The fourth power of absolute. Huh? No, it's enough. The maths that you know is enough. to understand the proof of this, but it's very involved. Now, so this is the heat flux. This is the heat flux through a surface in the form of radiation, which is proportional to the fourth power, and bodies that exactly subscribe to this are called perfectly black bodies. This is the emission in the form of thermal radiations. And if they are in the form of electromagnetic waves, then they have a certain wavelength. This energy has a certain wavelength. In fact, this total amount of energy, these many watts per meter squared, contains all possible wavelengths. Starting from lambda equal to 0 to lambda equal to infinity. This total amount of watts per meter squared that's emitted from the surface contains all possible wavelengths starting from lambda equal to 0 to lambda equal to infinity. So there is a thermal spectrum starting from lambda equal to 0 to lambda equal to infinity. All possible wavelengths are there. Yes, some of them are in the visible range. Roughly around close to 0.4 to 0.7 microns is actually the thermal radiation. However, real bodies, this is only a perfectly black body. Real bodies, when they are at absolute temperature T, then the radiations that they emit would not be sigma T to power 4, would be some epsa sigma T to power 4. Where epsa is the emissivity of a real body, and it lies between 0 and 1. Epsa equal to 1 for a perfectly black body. Emissivity means what fraction of the perfectly black body signal is being emitted at the same temperature. So if this is 0.5, that means 50% of a perfectly black body is what it emits. This is the model for a perfectly black body, but for a real body, it's going to be epsa times what it is for a perfectly black body, right? Essentially, at a given temperature T, the emission characteristics as a function of the wavelength, like I said, all wavelengths are included in this. All possible wavelengths are included in this, right? So as a function of wavelength, this is how this is called emissive power. At temperature T, as a function of wavelength lambda, this is what it really means is this is like watts per meter squared per unit wavelength. Let me explain this to you, what this E lambda actually means. This is at a temperature T where watts per meter squared per unit wavelength for various values of lambda. So in this case, say I have lambda equal to 0, lambda very large, and there is an intermediate lambda, and I take so this is a continuous spectrum. When a black body emits radiations, it emits radiations of all possible wavelengths, lambda equal to 0 to lambda equal to infinity. If I take a certain wavelength lambda, then there is a small band around this. Lambda plus d lambda is a small band around this. Now when I say the emission at lambda is E lambda, what it really means is the watts per meter squared per unit wavelength surrounding lambda. Watts per meter squared per unit wavelength surrounding lambda is E lambda. What it means is that over this d lambda, what's the energy that is radiated? That means watts per meter squared. How much watts per meter squared is emitted over this wavelength lambda to lambda plus d lambda? It's going to be E lambda into d lambda. You know what I'm saying? When I say the watts per meter squared per unit wavelength at lambda is E lambda. Per unit wavelength surrounding lambda. That means at lambda, if it's E lambda, then the total energy contained in a spectrum from lambda to lambda plus d lambda, this is energy per unit lambda. So over d lambda, this would be the energy. This would be the energy, right? So this is E lambda energy watts per meter squared per unit lambda per unit wavelength surrounding a certain lambda. That's what it means. This is the energy over this from lambda to lambda plus d lambda. This is the energy. These many watts per meter squared, right? So the total area under this curve, lambda equal to 0 to infinity. The total area under this curve, E lambda, d lambda, would be sigma t to power 4. Absolutely would be. This is the total energy, watts per meter squared, which is sigma. This will be proportional to the fourth power of the temperature. This will be proportional to the fourth power of the temperature. The area under this bell-shaped curve is going to be sigma t to power 4. Right? Now, at lower temperature, now E lambda peaks at a certain lambda. At lambda m, it peaks. That means there is maximum energy in and around wavelengths lambda. That means close to lambda m. The energy, the watts per meter squared is maximum. That means the intensity is maximum around some wavelength lambda m, right? At smaller temperatures, so this is, let's say, T1, at temperature T1. Okay. If I increase the temperature of that black body, then the variation could be this. This would be a lower curve for T2 less than T1. Sorry. In a general sense, this is T2 less than T1. And this varies, this peaks at some lambda m prime. This peaks at some lambda m prime. Whereas this peaks at lambda m as go on decreasing the temperature. As you go on decreasing the temperature, then at higher and higher wavelengths, do you find peaks of E lambda. That means if you know what I'm saying? If you decrease the temperature, then the maximum intensity is obtained for higher and higher wavelengths. That means for longer wavelengths, You know what I'm saying? At smaller temperatures, higher wavelengths are preferred for higher intensities. The maximum intensity is obtained at higher values of lambda for lower temperatures, In fact, lambda m is the wavelength at which the intensity peaks, right? So if a certain radiation takes place at temperature T, let's say this is at temperature T, and its intensity peaks at lambda m, then it's found that lambda m into T is a constant. Which means lambda m into T1 must be lambda prime m into T2. And this constant is called Wien's constant. And this law is called Wien's displacement law. This is called Wien's displacement law. Lambda m into T equal to constant, and its value is found to be 0.282 centimeter Kelvin. 0.282 centimeter Kelvin. Sometimes they use this as 0.3, sometimes they use it as 0.29, based on the problem. Whatever is more convenient in terms of calculation, some 0.3, 0.29, etc. So this is Wien's constant 0.282. Again, there is a formal mathematical proof of this. Just in case you want to know, I can share the material with you. But this is not just purely experimental. It has a proper formal mathematical proof, right? Lambda m into t equal to, where t, of course, remember, must be in Kelvin. T must be in Kelvin. So this is Wien's displacement law. In fact, this is the emission characteristics of. Sometimes, let me just tell you one passing reference. It's important to know this. Can I wipe this off? Can I just wipe this off? I know it's a little hot. We're talking of radiation. Had to be a little hot, right? Even at the same temperature, these emission characteristics are different for different bodies. In fact, they are not only emission characteristics, they are also absorption characteristics. This E equal to sigma T to power 4, where T is the temperature of the body and sigma T to power 4 is the watts per meter squared that is radiated. In contrast, if T is the temperature of the surroundings, if there is a body, let's say a perfectly black body, and T is the temperature of the surroundings, then it will absorb heat in the form of radiation. It will absorb heat in the form of radiation, which will also be of the form sigma T to power 4, So this is not only the emission characteristics, the sigma T to power 4 is also the absorption characteristics. Absorption also takes place commensurate with sigma T to power 4. So, if there is a body, let's say at temperature T1, then there would be simultaneous emission as well as, let's say a perfectly black body, a simultaneous emission as well as absorption. So, the emission here would be sigma T1 to power 4 watts per meter squared. The absorption here is going to be sigma T to power 4 watts per meter squared. Right? So, if this is larger than this, there would be emission. There would be net emission. And if there is net emission, it will lead to cooling. If T1 is bigger than T, it will lead to cooling, net cooling. Simultaneous emission as well as absorption takes place. That is the important thing. Now, so whatever I drew in terms of that bell curve, which was an emission characteristics, is also the absorption characteristic for a given material at temperature T. When in paper mills, do you know how the whole thing functions? The cooling, there is this wet paper coming down the rolls, and it has to be dried. Now, the drying of that paper does not take place by exposing it to 2000 degrees centigrade and melting it away to glory, right? There is soft heating. Again, you can't expose that paper to fluid at high temperature or fluid at lower temperature and do things, right? You can't expose it to fluid. You can't do a conduction heat transfer. You can't do a convection heat transfer. So to dry that up, what's actually done is this radiative heat transfer. There are hot radiant tubes inside a furnace, and paper passes through rolls of that furnace. And so there are two things. The radiant tube emits heat, paper absorbs heat, right? So there is a radiation heat characteristics associated with the radiant tube, and there is a absorption characteristics associated with the paper. Simultaneous things, right? Now, what is it that you would like? You would want, for maximum or the most efficient mode of working, you would want that the absorption characteristics of paper is very similar to emission characteristics of the radiator. That's when there is best drying of paper. So the radiant tubes that are modeled and are created are based on this premise. So they would tell you, well, paper has, it's wet, paper has this characteristic, and the radiant hot tube, which is at a high temperature, will have this characteristic to dry up the paper. So what they would look at is, they will try and match these bell curves to the extent they can, so that there is optimum and best utilization of heat emitted by the radiator. So this is the major problem of radiant heat transfer, where they have to match the emission and absorption characteristics of the entities involved. So this bell curve, has to be taken care of. Now, again, see, let's say, have some more patience. I know you might get really heated up at this point of time, and they could thermal breakdown. But one important thing to understand is that if this is a body at temperature, say theta, and the surroundings are at temperature theta naught, and theta is greater than theta naught, theta is greater than theta naught, then there would be simultaneous radiation, which is, and there is absorption, right? Emission as well as absorption would take place. Essentially, the rate at which cooling takes place will be proportional to sigma theta to power 4 minus theta naught to power 4 would be the rate at which cooling will take place, right? Cooling will take place proportional to this, yes or no, right? So this would be like, if A is the area of the surface, then these many watts are being eventually radiated out, and this must be equal to mass into specific heat into d theta dt with a minus sign. Why? Because theta is decreasing with time, it's cooling, right? Now, binomially, you can check that out for yourself, that if theta minus theta naught is small, if the difference between the temperature of the body and the surroundings is small, then we can show that this will be almost proportional to theta minus theta naught. This will almost be proportional to theta minus theta naught. If theta minus theta naught is very small, then d theta dt, this is the rate at which cooling occurs, d theta dt will almost be proportional to theta minus theta naught. If the difference between the body and the surroundings is not very large, then theta minus theta naught, and this essentially is Newton's law of cooling. Newton's law of cooling. He didn't spare anything in maths and physics. See, he was there everywhere. So this is the rate of cooling. So essentially, say the surroundings are at temperature theta naught, which is not going to change significantly with time, but theta will change significantly with time, right? And let's say theta minus theta naught is small, then d theta dt essentially would be some minus c at any given instant of time, theta minus theta naught. Let's say theta was initially theta 1, and then after a while it becomes theta 2. Theta was initially theta 1, after a while it becomes theta 2. And I want to find the time the temperature of this body changes from theta 1 to theta 2. So at any given instant of time, this would be d theta dt would be, let's say, minus c times theta minus theta naught, right? And what this would mean is, I could integrate this, theta by theta minus theta naught is minus c dt. At time t equal to, say, 0, theta was theta 1. At time t equal to 2, theta becomes theta 2. Right? So this will give me theta a function of time. This will give me, let's say, theta 2 to t. This will give me theta a function of time. So I can find out the time it takes for the body to cool from theta 1 to theta 2. If you plug in theta equal to theta 2, you will get the time it takes for it to cool to theta 2. But you don't do all this. This is very ornamental. We just don't do all this. I'll tell you what you should be doing, and that will work in an examination, because in an examination you will not get logarithmic values. It will become horrendous if you do this. In an exam, just very quickly, what you want to do is, say they tell you that the surroundings are at 20 degrees centigrade, and this body is initially, let's say, at 30 degrees centigrade. And they say the time taken by this body to cool from 30 to 25 degrees. The time it takes for this body to cool from 30 degrees centigrade to 25 degrees centigrade is, say 1 minute. Is 1 minute. Find the time it takes for it to cool from 25 degrees centigrade to 22 degrees centigrade. Find the time it takes for the body to cool from 25 degrees centigrade to 22 degrees centigrade. Say they tell you it takes 1 minute for the body to cool from 30 degrees to 25 degrees. Find the time it takes for the body to cool from 25 to 22 degrees. Don't do all this. Although this is right, but shouldn't do this. What you could do is, in this case, what's the total cooling that takes place? 5 degrees in 1 minute. So 5 degrees per minute. 5 degrees per minute is the rate at which this cooling takes place. That must be some constant C into the temperature difference. Now, what's the average temperature of this? 27.5 is the average temperature of this. So what's the average temperature difference between the body and the surrounding? 7.5. See, the average temperature here is 27.5, right? So the average temperature difference is going to be 7.5. So then I say the rate of cooling, 5 degrees in 1 minute, is C into 7.5 is the average temperature difference, right? C I do not know. Okay, that's for this situation. Now come to this. The C will be the same for both the situations, because it's the same body that we are talking about. Now when I talk of this, what is the total cooling? 3 degrees, let's say in time t. 3 by t degrees per minute. 3 by t degrees per minute, right? That must be some constant C. What's the average temperature here? 23.5, right? What's the average temperature difference here? 3.5. Divide this by this and solve for t. That's the time. Now, obviously, many things wrong about this. Because, that's not the average temperature, etc. But, tell you something very simple. The temperature that you get, the time that you get out of this and the time that you get out of this in minutes will differ only, if at all, in the second or the third place of decimal. So the error produced by doing this nonsense is very little. So do this. Right? This is wrong, but right. Right? So it makes sense to do this. So that was a very, very quick, brief outing on radiation heat transfer. There are some problems. We'll look into this in the next class. See you then on Sunday, same time, 10 o'clock. Right? Does it make sense to all of you?
So we can make it 9:30.
Yeah, sure. Okay, 9:30 then on Sunday. Thank you.